Alright, in this video we're going to talk about vectors, and basically we're going to start with just defining what a vector is. A vector is basically the quantity or a quantity that has both magnitude and direction, such as force, velocity, or acceleration. Okay? When we use the term magnitude, we're talking about the length, and then it has a direction as well. So for example, the quantity 6 miles per hour is a regular number or scalar. The quantity 6 miles per hour to the northwest is a vector because it has both size and direction. Some key points that you need to know for this unit are: a vector is a directed line segment, PQ, with an initial point P and a terminal point Q. A vector has a magnitude, the length, and a direction. Magnitude is denoted kind of with the absolute value bars around PQ. Two directed line segments have the same magnitude and direction are equivalent regardless of their location. The set of all directed line segments equivalent to the direct line segment PQ is the vector V, which equals PQ. Vectors are denoted in the book with bold lowercase letters, usually U, V, and W. We indicate vectors as U, V, and W when we're writing them. Okay, what makes two vectors equivalent? They have the same magnitude and direction. Okay, so here if we let U be the vector represented by the directed line segment from R, 7, negative 3, and S, 4, negative 5, and V be the vector represented by the directed line segment O from 0, 0 to P, negative 3, negative 2, prove that U is equivalent to V. Okay, so what we're going to do is, first of all, recognize that U, our vector U, is RS, and our vector V is OP. Okay, so if we were to graph these two vectors, RS is from 7, negative 3 to 4, negative 5. Okay, so our vector, here's R, here's S, goes from R to S. And our vector OP from 0, 0 to negative 3, negative 2. Okay, so basically we are proving that these two vectors are equivalent. So the first thing that we need to do is talk about their magnitude, okay? Now magnitude refers to their length, so we're going to be using the distance formula, okay? So the magnitude So let's start with the U vector. So we're going to find the magnitude of RS, which is going to be the square root of 4 minus 7 squared plus negative 5 minus negative 3 squared, which when you calculate that, you end up getting the square root of 13. Okay, then we'll do the magnitude of V, which is from OP. So in this case we have negative 2 minus 0 squared plus negative 3 minus 0 squared, which ends up giving us the same negative 13, or sorry, square root of 13. So right now all we've done is we've proved that their magnitudes are the same. The second part here is we needed to prove that they're going in the same direction. Okay, so to do that we're going to look at their slope. Okay, so our slope of vector U, our slope is going to be negative 5 minus negative 3 over 4 minus 7, which gives us negative 2 over negative 3, which is 2/3. Same thing with V. We're going to find our slope of V, which is going to be negative 2 minus 0 over negative 3 minus 0, which also gives us negative 2 over negative 3, 2/3. So in this case, we have just shown that our two vectors have the same magnitude, so they have the same length as the square root of 13, and they're both going in the same direction because their slopes are the same, 2 over 3 and 2 over 3. So since they have the same direction and same magnitude, vector u is equivalent to vector v. Okay? All right, on the next page, we're going to talk about how you represent vectors. Okay? So, basically, we're going to talk about a couple different things. The first one is going to be the standard position. This is the initial point of the vector is at the origin, okay? So in the previous example, OP would be a vector in standard position because it started at the origin of 0, 0, okay? If the initial point of your vector is at x1, y1, and the terminal point is at x2, y2, then the component form is going to be, of the vector v, is going to be x2 minus x1, y2 minus y1, which is going to give you your vector v1, v2. Okay? The vector v1, v2 is called the position vector of the point v1, v2. Okay? So basically, this is how you would just take any vector and put it into standard form. Okay? To find the component form in this first example, and the magnitude of the vector PQ, where P is negative 2, negative 2, 2, and Q is negative 2, 5. So basically, we have this vector PQ, and we're asked to put it in component form. Okay? So if we sketch this, we're at negative 2, 2, and negative 2, 5. So right now, our vector looks like this. Okay? So we want to change this so that it's in component form and then find the magnitude, okay? The reason why you want to find the component form first is because it's a little bit easier to find the magnitude once you have it in component form, okay? Okay, so what we're going to do is we're going to find the form of this. We're going to take negative 2 minus a negative 2. And then we're going to take 5 minus 2. So our component form of this vector is going to be 0, 3. Okay, so this is the component form of our vector. Then, to find the magnitude, all we have to do is basically take the square root of our first term squared plus our second term squared. So in this case, we would have a magnitude of the square root of 9, which is 3. Okay? So if we put it in component form first, finding the magnitude is going to be a lot easier since you don't have to subtract your values. You can just square both of them and then take the square root. Okay? All right, why don't you try number 2 by yourself? All right, vector operations. These can be done graphically or algebraically. Okay, so adding and subtracting is going to be the easiest one for us. And basically, we can take a vector u and add to it a vector v. Okay? Here is a general equation that you could use to do it algebraically. To graph it, what we're going to do is we're going to graph both of these vectors. Now, both of these vectors are in component form, which means they go through the point 0, 0. Okay? So our first one is negative 1, 3. So we start at 0, 0, and we go negative 1, 3. So that's going to be our first vector. Okay, our second vector is 4, 7. So we're going to start at 0, 0, and we're going to go 4, 7. and that's our second one. Now, to find the sum of this graphically, what we're going to do is kind of create like a little parallelogram, I guess. So we are going to sketch this, basically take this vector and sketch it right here. Okay, so from this we go to the left one up 3. So I'm going to do the same thing here. Left one up 3. Okay, so this here is parallel to this here. Okay, you can do the same thing with this line. What it ends up doing is coming straight up like this here. So this point here is going to be the sum of our two vectors. So if we take vector u plus vector v, we're going to get 310. Okay, so that's how you would do it graphically. If we want to do it algebraically, we're just going to basically plug it into this equation right here. So we would take u plus v is equivalent to, and we're just going to add these, -1 plus 4 and 3 plus 7, which gives us 310. Obviously, algebraically is going to be a lot easier and quicker for us since we're just adding our x's, or sorry, our first terms and adding our second terms. Okay. All right, on the next page, you can do u minus v. This is going to be very similar to the adding one. I'm going to let you guys try this one, but basically you should get u minus v to be equivalent to -5, -4. Okay, I'd like you guys to try that both algebraically and graphically here. The next thing that we're going to talk about is scalars, okay? Basically, the product of a scalar k and the vector u is k times the vector u. So this formula here is very straightforward and it's very simple. So all you're going to do is just plug stuff in, okay? So if we want 3 times the vector u, we're going to take 3 times -1, 3. And basically all we do is get the vector -3, 9. Okay? Same thing here, you're going to, and I'm going to let you guys try this one by yourselves, you're going to take 2 times the u vector and then add it to 3 times the v vector. When you do this, you're going to end up getting 10, 27. I want you to try number 2 by yourself. Okay, when would you use these scalars? This is just kind of a side note, but basically you would use these scalars if you're trying to find the force of something. So if you're taking your mass, which would be a scalar, and multiplying by the acceleration, which would be your vector, you're going to get your force vector. Okay, so you're going to use scalars when you're finding force, which is mass times acceleration. That's one example. All right, real quick, some special vectors. Okay, the first one is our 0 vector, that's 0, 0. The second one is our unit vector. These are important because our unit vectors have a length of 1. We are going to be asked to find the unit vector of certain things. Basically, the vector u is equivalent to, u representing our unit vector, is equivalent to the vector v over the magnitude of v. Okay, this is called our unit vector in the direction of v. Okay, so for example here, if v equals -3, 2, verify that v over the magnitude of v is a unit vector in the direction of v. Okay, so we're going to do this kind of in steps here. We need to first find the magnitude of v. In this case, the magnitude of v is going to be the square root of -3 squared plus 2 squared, which gives us the square root of 13. Okay, so our magnitude is the square root of 13. So to find our unit vector, what we have here is our vector -3, 2 over the square root of 13. Oops, 13. Okay, if we write that out, that's going to be the same thing as negative 3 over the square root of 13, 2 over the square root of 13. Okay, so this here is our unit vector. What we are asked to do here is prove that our unit vector has a length of 1. So to do that, we are basically going to take the magnitude of this. Okay, so the magnitude of negative 3 over the square root of 13, 2 over the square root of 13 is just going to be the square root of negative 13 or 3 over the square root of 13 squared plus 2 over the square root of 13 squared, which is going to be 9 over 13 plus 4 over 13, which is the square root of 13 over 13, which is 1. So this, in fact, is our unit vector, and it has a magnitude of 1. So what we've done here is we basically just proved that a unit vector has a magnitude of 1. Okay? Remember, it's still going to be in the same direction as V,